Okay. So find the area section is not too bad. You just got to understand the formulas and the notation. Excuse me, the notation. So let's go over the notation real quick. So sigma notation. The sum of n terms. Let's call them A1, A2, A3, all the way till AN is written as the following. So the sum as I equals to 1 all the way until n. So A sub I is equal to, so this is the notation, right? This is telling you start at 1, the index. So the I is going to be 1 and go all the way until n. So 1, and then the sigma, capital sigma means sum. So add these terms. So 1, 2, 3, all the way until you get to the nth term. Okay, so where I is the index of the summation, A sub I is the ith term of the sum. And the upper and lower bounds are n and 1, respectively. Okay. Oh, excuse me. So this is real quick, do an example. It's not that bad. So if I tell you to go from sum the terms starting at k equal to 3 all the way until 5, and the formula that I'm giving you to do this is k over k plus 2. So this will become 3, so plug in the 3, and then cycle all the way until 5. But you gotta add them all up. Do you see how the notation works? So start at 3, go all the way until 5. Of course, you would add these fractions, but I don't really care about that right now. Do you understand the formulas? Okay. All right. Well, so that's why you use the formula and the summation symbol. So now there's going to be examples as well that gives you a pattern, and they ask you, use a sigma notation to write the sum. Okay, so here's the pattern. 3 over 1 plus 2 plus 3 over 2 plus 2 plus 3 over 3 plus 2 all the way until 3 over 11 plus 2. So what is the summation formula going to be? We'll use K again, I guess. So what do you see changing? And what do you see that's fixed?
Yeah, the first number 1, then 2, and then 3. And then the fixed number is just that +2.
Yeah, so this is the variable part, right? So what is the first number though? Or where do we start the index, I guess? And where do we stop? So this would be 1 to 11. The 3 is just chilling there, so just put it. The one that's changing is going to be the variable. Nothing else changes, right? Does that make sense? So just basically look at the patterns and try to figure out how do I change it into this form and also be able to use this form and get terms. Any questions on example 1 and 2? Okay, I'm going to give you a bunch of formulas. Number 1. All right, so if you're summing I to n, 1 to n, and it's just a single I, is going to turn into this, whatever n is. If it is n, then just change it to n. But if it's a number, then plug in that number here. Okay, now if you are doing a sum of squares, then the formula will be n times n plus 1 times 2n plus 1 over 6. If you're doing a cube, summing a bunch of cubes, you're going to get n squared times n plus 1 squared over 4. And then the easiest one, if you're going to sum any constant n times, so some number c, and then it's just going to be c times n, where c is any real number. Okay, so what you want to do is use these formulas to help you out. I think we should do the next one on the next page. Next example. Yeah, let's do it over here. We'll turn back in a sec. Okay, so evaluate this guy and then change n to 100,000, 10,000. So what you want to do is apply the formulas. And then once you have it all simplified, then plug in these numbers. So first things first, this n squared doesn't match the index. So you can pull this out and treat it like a constant. So there's a couple of properties of summations. Well, basically all the properties of integrals are the same properties for summation. Okay, so you can pull out constants. So I'm going to pull out this 1 over n squared. Here. Okay. Next thing I'm going to do is separate this as, oh, I'm sorry, I already removed the n squared. This will be I plus 1. So what you can do is just separate the summations into two separate ones for I and the constant 1. So now look at the formulas. We have one for I and we have one for constants, right? So just change the one for I into this and use the number 4 for the constant. So RC happens to be 1. So this becomes n times n plus 1 over 2 plus n. Technically 1 times n, right? That's C is 1. We use 1 and 4 right here. Does that make sense up to this point? Okay. So now just do some algebra and then plug in the numbers. That's it. Let's go ahead and add these together. So this LCD is 2. So I need 2n over 2 in order to combine them. Then we get, if I distribute, well, let's go and do it in 2 steps. Okay. So multiply this in, combine like terms, and we're going to get n squared plus 3n over 2n squared. Factor your n, you get n plus 3 over 2n squared to cancel one of these. And finally, we end up here. All right. Any questions on the algebra or using the formulas? Okay. So just plug in the numbers and you would be good. So n equal 100, that would be 103 over 200, right? N equal 1,000. That would be 1,003 over 2,000. N equal 10,000 would be 10,003 over 20,000. Can you guys see the homework? This is 5.2. So here it starts off with just plugging in numbers, doing the summation like example 1. Here they use the basic formula. This will be equal to, well, here it starts at 0. Notice that the formula we have is supposed to start at 1. So we would have to adjust. And this one right here is the one we did on the second example. Find the pattern, right? You see a constant third. The only thing cycling is that 1, 2, 3, all the way to 17. So it starts at 1 and goes all the way to 17. The pattern is going to be 1 over 3i, whatever index they're using. Okay. Same thing here. Pattern is the +1, +2, +3. So that's going to be the I part right here. Index starts at 2. Actually, sorry, starts at 1, goes to 11. This one's going to be simply using formula 4. This is equal to C times N, where C is 7, N happens to be 7, which is 49. Here they use equation 1, but they factor the 2 out first. Once they have it, then they plug in 24 for N. So basically you're going to have this on this question. You're going to end up with this one. So they have 2i, right? So pull out the 2 in front. The I becomes this. You just have a 2 right there. And then you plug in 24, and you're going to get 600. Do you see what they did on number 6?
Can you repeat that, Professor?
Yeah, let's go ahead and work it out real quick. It's real simple, so I want you to see it. So the sum starting at I equal 1 to 24 of 2i. So basically what I'm saying is pull out the 2 and ignore it for now. Use the formula, so that's going to be 2 times the formula thing, n times, I forgot what it was, n plus 1, right? Yeah. These 2's will cancel, leaving me with n times n plus 1, but what is n? N is 24. So this is actually 24 times 24 plus 1. So 24 times 25. Whatever that is. They said it's 600. I don't know if that's true or not.
Yeah, it's
600? Excuse me. So all you got to do is do your algebra and then use these formulas. Let's see. Let's do number 9, and that'll be the last example for this section. From the homework. So we have the limit as n approaches infinity of the sum I equal to 1 to n of 4 over n cubed times I minus 1 squared. All right, so what you want to do, deal with the limit at the end. First, deal with the I stuff, okay? You can pull out the well, let's see. Let's take it slow. So if you multiply this out, you're gonna get I squared minus 2i plus 1. Apply your formulas. We have an I squared formula, we have a 2i, but let's go ahead and separate everything first. So this is way out here. I'm working in here for now. Use a formula for I squared. This negative 2, I'm going to go ahead and pull that out in front. Deal with the I. Deal with the constant. We have formula for all 3 of those. Okay. So I squared formula. Let me see it. This guy right here is going to become n times n plus 1 times 2n plus 1 over 6 minus 2 times the I will become n times n plus 1 over 2 plus, this is a single 1, I forgot to write it. That will simply be 1 times n. Okay. Real quick, before we go any further, what's the degree of this first fraction right here? Can you tell? Of the numerator? And there's three factors, three linear factors. So it's going to be degree 3. If you FOIL all this garbage, the highest power that you could get would be a cube. You have a bunch of other stuff, but the biggest one will be a cube. Biggest one here will be a square. 2 factors. This is a single degree, right? Degree 1. So if I were to multiply it in, this 4n cubed, and then take a limit, we can base it off use the idea of degrees or L'Hopital to help us out. So 4 times this, n cubed times that, 4 times 2, n cubed, 4n cubed times this guy would be 4n over n cubed. All right. Do you agree if I take the limit that these two will go to 0? Do you see why?
Is it the negative?
It's because the power on the bottom is bigger. So this is going to grow faster. This will grow faster. So when you take the limit, these will be 0. These have the same degree. So we say when they match up, you just take the coefficient. So the answer would be 4 over 6. So from here to here, summation formulas. Here we took the limit. That's how they get the 4/3. Oh, wait a second. I got a 6. Let me double check the formula. Oh, I see why. This is a 2 right here. This should be 8, which would be 4/3. It's hard to see unless you multiply this out. But you'd end up with the coefficient of the highest power would be 8/6. So you would take the coefficients. But anyway, all we're doing is applying the sum formulas and then taking the limit rules that we've been using this whole time from chapter 2, or you could do L'Hopital if you want to. But if you do L'Hopital, I would FOIL it out first because doing it right now would be a bunch of product rules, which I don't recommend. But I think using this idea is easier. It's up to you. All right, so that's 5.2. So we're going to skip 5.3. I believe I'm going to it should be removed or will be soon. We're going to 5.4. You guys cool on 8.2?
Hey, Professor, I'm sorry. Just real quick on that 0 and 0. You if you calculate that, you said it's eventually it's gonna become 0 or
Oh, which one? These?
yeah, yeah.
Yeah, the
How,
limit of these two are 0.
so as the limit approaches, is that infinite negative
Yeah,
infinity?
this is as n goes to infinity, these will
So
go to
it's
0.
gonna go to 0. Okay, I got you. I got it. Thanks.
Mhm. And since these degrees are the same, you're going to be left with the leading coefficient being divided by each other.
So on the test, are we gonna be allowed to use these formulas, or do we just write them like on a sheet of paper, or
Yeah, you can bring the formulas with you and just put them on your formula sheet. Okay, moving on then. So final section, 5.4. The fundamental theorem of calculus. Okay. So if a function f is continuous, on the closed interval a to b and capital F is an antiderivative of f on AB, then the definite integral of from A to B of lowercase f of x is equal to the antiderivative at B minus the antiderivative at A. Oops, I forgot to put dx. Dang it. There we go. Okay, so basically what you do is you find the antiderivative and then you evaluate at the upper bound minus the lower bound. That's it. So for example, evaluate the definite integral. So the integral from 0 to 4 of 3x minus 1 squared dx. So we got to find the antiderivative of this first and then plug in 4 minus plugging in A. The only issue is we should probably square this first so we can deal with it better or easier. Squaring this would give us 9x squared minus 6x plus 1. Now, integrate. Remember, we said we can separate the integral on each one. All right, so what is the antiderivative of 9x squared? You guys remember? Excuse me. That would be the regular derivative. Remember, anti means you gotta do the opposite. We do 2 plus 1 over 2 plus 1. The power rule for antiderivatives. It's the same thing here. 1 plus 1 over 1 plus 1 plus this will just be an x. So once you've done all of them, you can just write it this way. I'm going to evaluate from 0 to 4. Okay. So that'll be 9x cubed over 3 minus 6x squared over 2 plus x from 0 to 4. Okay, so then we get 3x cubed minus 2x squared plus x, just reduce it. from 0 to 4, so that would be 3 times 4 cubed minus 2 times 4 squared plus 4 minus 3 times 0 minus 2 times 0 plus 4. This is what the fundamental theorem is saying. Do the antiderivative first, and then plug in whatever number's up here first, minus the number, minus whatever you found as the antiderivative at the bottom one. So we found the antiderivative to be this, 3x cubed minus 2x squared plus x. Just plug in the 4, minus plug in the 0 here. Does that make sense with what they're doing? Any questions on the first one? Okay, cool. Let's do an easier one this time. I feel like that one might have been a harder way to start out here. Let me see. Let's do the integral from 0 to 3 of x plus 2. So integrate each term separately. So antiderivative of x, right? The rule says add 1 to the power and then divide by that same thing. That's the power rule. Antiderivative of a constant is just going to be that constant times x. Then evaluate from 0 to 3. So once you do the antiderivative, you stop writing the symbol. So we get x squared over 2 plus 2x from 0 to 3. That'll be 3 squared over 2 plus 2 times 3 minus 0 squared over 2 plus 2 times 0. So I'm just plugging in the upper bound into the derivative, or the antiderivative, and then minus that same antiderivative at the lower bound here. This, of course, is 0. This would be 9 halves plus 6, 21 halves. Any questions on any of these steps here?
What number was this on the homework?
I don't know. Let me see. This one will look like I think I might have just made that one up. I don't see it in there. I made an easier one just because the last one was kind of hard. The homework starts off kind of difficult. So I made this one. It's a little more simple.
Okay, this is you said this is 5.4, right?
Yeah.
I'm sorry, I stepped away for a few minutes.
No, you're good. Yeah, it's 5.4. This is the gist, right? You integrate each term. Once you have the antiderivative, you plug in the upper bound first into the x's, and then minus the lower bound into these x's here. This is 0, so add these up, you get 21 halves. And that's it.
Gotcha. This is kind of similar to what we learned on Tuesday.
Yeah, we're using this. It's the same thing from Tuesday, except we have definite values here. So you notice how we're not doing plus c anymore? That's because we have these bounds. So this first one, right, you do the antiderivative, which is going to be x squared. And then you plug in 4 minus 0. Number 2 is like the first one we did. You just got to multiply it out and then integrate each term. So they're all going to be the same. It's just different types of algebra. Like here, number 3, you want to bring up the u to the top and then integrate or do the antiderivative of each term. Change this to a power and simplify the fraction, and then do the antiderivative of each term. But eventually they want to apply it to area. Excuse me. Here. Let's do let's go ahead and do 11 and 12, I guess. So since they gave us a picture. So let me put it one more time. They're telling us to find the area underneath cosine, right? Which is this shaded region from 0 to pi over 6. So this is telling you that we should be integrating from 0 to pi 6. And then you do the cosine. That's the upper part here. Minus the bottom part, which is just a 0. So the 0 doesn't matter in this case. It'd be d dx. Okay. So you're basically creating this and then solving it using the graph. All right, so the integral from 0 to 1, sorry, I think I said pi over 6, 0 to pi over 6 of the function cosine minus 0. So it's always when you look at the graph, it's always going to be the upper bound minus the lower bound. So what I'm saying is this upper piece minus the lower piece. So the upper part is the cosine, bottom part is the 0. So just integrate this guy. Antiderivative of cosine is going to be sine x. And then go from 0 to pi over 6. So this will be sine of pi over 6 minus sine of 0. What is sine of pi over 6?
Wait, are we taking the derivative of cosine x or just?
Antiderivative.
Oh, okay.
Doing the opposite. Chapter 5 is all about doing the opposite of the derivative.
And so we're looking for sine pi 6.
Yeah. It's going to be that 1/2.
Um, yeah, it's 1/2.
So it'll be 1/2 minus 0. So the area underneath is a half. So one application of antiderivatives is finding area underneath curves. Okay. Let me do another one for you. Example 4. Find the area of the region bounded by the graphs. Of the following equations. So basically they're telling you that there's a region, just like we had that picture earlier, bounded by the following. So they're not giving you the picture. You have to graph it yourself. So bounded by this parabola, by the vertical line x equal to 0, the vertical line x equal to 3, and the horizontal line y equal to 0. So bind all of these together, and you'll have a section. Okay, so just do a sketch. So the parabola is going to be doing the x equal to 3. Let's say 3 is right here. Vertical line going this way. 0 is right here, so it'll be bounded there. So we have some parabola doing this. And then we're bounded by y equal to 0, which is down here. And x equal to 0, which is over here. And bounded on the right by this vertical line. So the section that we're enclosing is this. So let me use a grapher so you can see it a little prettier. There, so you can see it better. Here's the purple line is y equal to 0, the horizontal line. So let me see if I can zoom in better. So the shaded region is all this. See what I mean? So I want to integrate the top, this whole, I need to find the area of this region by using the integral. In order to do so, you integrate the top part, which is a parabola, minus the bottom part, which is this line. But the bottom is going to be 0 again, so it's not a big deal. So you would write the top part, which is the parabola, minus the bottom. So the integral from 0, because we're starting, there's this idea about rectangles. So I'm getting infinitely small rectangles in order to find the area. But if you draw a little rectangle, do the top line as bottom, that means you're doing dx because the rectangle thickness is on the x. So the top is this guy minus the bottom, which is just 0. And I'm going to go from 0 to 3. That's where the region ends, right? So all I have to do is integrate from 0 to 3, 2x squared plus x plus 2. And that will give me the area of this shaded section. So antiderivative of each term, and then plug in the 3 and the 0. The antiderivative will be 2x 2 plus 1 over 2 plus 1 plus x 1 plus 1 over 1 plus 1 plus 2x from 0 to 3. So that will be 2x cubed over 3 plus x squared over 2 plus 2x from 0 to 3. So just plug in the numbers and you're good. Okay, I'm out of space here. This will be something 57 over 2. Okay. When you get the general idea what they're doing, you're kind of uh, closing stuff off. So make sure you first are comfortable with the antiderivatives in 5.1. Once you're comfortable with that, then you can start applying it to this. So first step is get good at antiderivatives, 5.1. Then get comfortable evaluating these types using the fundamental theorem of calculus. Once you're comfortable with these, then start doing these applications. If you're still struggling with the antiderivative, then this will feel much harder because you're not there yet. Do you have any questions about 5.4? No, I know there's a lot of moving pieces, right?
It looks easy when you explain it, but then when it's time for the homework or something, it's
Yeah, just make sure you got 5.1 down before you try 5.4. 5.2 is kind of a separate thing. But it helps to understand the summations because the section we skipped is 5.3, and that talks about the rectangles, but it's very tedious, and it's the long way of doing things. Like we did the limit rule for derivatives, so you would have to find an infinite sum of rectangles to get the area. Then you do this method, which is easier. I'm trying to save you guys some time, but first practice that method, okay? All right, guys. Let me take roll. I guess it's the much else to say. Excuse me. All right. Abraham,
here.
Shamima, Isabella Carvajal, Kaylee Gill,
Here.
Frankie Huron, Angel King, Kaylin McCormick, Kimberly Mendoza,
Here.
Olivia Munoz,
Here.
Joshua Rabago, Devias Roberts,
Here.
Elias Sanchez,
Here.
Annalise Tidwell.
Here.
Okay. All right, guys. So this was pretty much our